Please go ahead.
Okay, thanks for the invitation. So this is the third and last talk in the series where we continue and we'll finish the proof of the wave-clear equation today. So first, let us recall the things we discussed in the last two lectures. So first, the problem, the setup of the problem. We have a non-Newtonian equation. We have a large box, a non-Newtonian equation on a large box, so size L, and we have a weak nonlinearity indicated by these parameters lambda. And here we set this lambda square equals alpha times L to B, where this alpha is strength of nonlinearity that goes to 0, and L goes to infinity according to some particular scaling law that will be specified in that slide. And here we're considering this delta, this Laplace operator, strictly speaking, we should consider irrational torus or generic irrational torus or twisting Laplacian, but the proof, most parts of the proof is the same, especially the proof for the part we're concerning about is the same. So let us just be simple about this this Laplacian. And now we assume the initial data. So here we're considering this non-Newtonian equation with a random initial data, and we're assuming the so-called random phase and amplitude assumption, which is saying that the Fourier coefficients of the initial data, this is normalizing constant, and the Fourier coefficients of the initial data is independent, and they have this particular strength given by a Schwarz function initial data, which is a Schwarz function, and either pair like identically independent Gaussians. They don't have to be Gaussian, but we're assuming Gaussian just for simplicity. Okay, so this is the setup, and then we're looking at the expectations of the you had where the evolution, the expected value of the evolution of these size of Fourier modes. And then the conjecture is that we have this expectation is approximated by the solution to the wave-clear equation plus an error term that vanishes in the limit L goes to infinity, alpha goes to 0. And here we are assuming this particular scaling law alpha equals L to minus 1, and that is the scaling law we're assuming throughout this work. And we can of course consider other scaling laws, and that will be the topic of future work. This result we're assuming alpha equals L to minus 1. Okay, and here this solution to wave-clear equation is rescaled up to this kinetic time scale, which is given by alpha minus 2. In our case, alpha equals L minus 1, so alpha minus 2 equals L squared. Okay, and moreover, this NPK is a solution to wave-clear equation. I'm writing it here, although we'll not be talking about this today. The NP is a solution to this evolution equation. dp of n equals this integral of this. So this is the delta of the resonance factor, and we have this cubic term. Okay, so this is just a review of the conjecture and a review of our conjecture and our theorem. And now the proof, for the proof of our theorem, we did in the last two lectures, we did some reductions, and we'll go over those two. So we start with the solution U, the non-Newtonian equation, and as a standard, we do a rescaling in time, and we take out the linear evolution flow, and we get this profile ALT. The delta is a small number, is represent the short time. This short time is independent of L. And then this AKT can calculate sense out this equation, so it's equal to initial data plus this integral. So the integral, and then this is the e to the delta pi L square omega as and with this cubic exponent A, this initial data given again by this random Gaussians, independent Gaussians, where omega is a familiar resonance factor here. Okay, and here in the sum here, there is a term where K1 equals K2 or K2 equals K3, the so-called resonant term, and those we can get rid of them by a further gauge transform. So which is kind of the meaning essentially we just if we consider the term where K1 equals K2 or K2 equals K3, you just get a term which is a mass term, and its mass is conserved, so you can just get rid of it by a gauge transform. So we're not running out, but in the in the next a subsequent proof, we'll always assume that K2 is not equal to K1, K2, so this is a non-resonant sum. Okay, so this is just it's a setup. And now, of course, we see that AKT equals initial data plus a Q return, and then the most natural thing we do is to iterate. We get this expansion of AKT with linear term plus cubic plus primitive and so on. And this this expansion is organized in terms of alternatives. Okay, so we do this expansion. And then this expansion will have a remainder. We'll not talk about the remainder today. It's kind of, there is one technical thing, but we don't have time to cover that. And then the main term is in this expansion, we're having this summing over this ternary tree T, or T is ternary tree of a scale at most capital N is going to be log of L as we specified last time. So here, this scale of a ternary tree means the number of branching nodes, the number of, this is one branching node, this is another, but this one has scale 2. Okay, and expression of this AKT we also discussed last time, that this is a plus minus 1 or plus minus I factor is not important, and this is the power here depending on the scale of the tree, and then you have a sum over all these Kn. Yeah, so Kn is like for all the nodes and of the tree, and this Kn here is assumed to be a derivation. Derivation means that if you have n, n1, n2, n3, then we must have a Kn equals Kn1 minus Kn2 plus Kn3. So at each branching node, we have such a linear equation, which is the natural one from the convolution structure of the cubic concatenation. Okay, so we're summing over all these declarations, Kn says on these equations, and here A is some function here. We'll see it later. And this T and omega n, this omega n got a resonance factor associated at each branching node. So here at this branching node, omega n is just like a mod Kn square, mod Kn1 square minus mod Kn2 square plus mod Kn3 square minus mod Kn. Okay, and we have this product, this initial data, and this is the function of Gaussian. There is a plus minus, it depends on the sign, but it's not, it will not be very important. This has to do with the pairing, like what pairing we can choose. Must have plus with the minus. Okay. So this is the expression here. We reviewed it last time. So here we have the sign, the scale, the factors. This L runs over all the leaves, and this is the declaration of the set and the okay, this is the expression we have in the tree term, and then if we take take two tree terms, we collapse them, we take the correlation, then we get the sum in terms of the couple. And that is what we have when we talk about the interpretation of AKT squared. If you look at AKT squared, then we are not summing over all trees, but we're summing over all the couples, where couple means we have two trees and together with the pairing between the leaves of the two trees. Okay, the couple means two pairing trees, which leaves completely paired. Again, we forget about the remainder. So we have these couples where we have this question KQ is essentially the product of the tree terms and the excitation. If this is a sign plus minus 1, this is again a power which depends on the scale of the couple. Again, the scale of the couple means the scale of the sum of the scale of the trees. And then we're summing over all the declarations. So here, let me emphasize that for declaration of a couple, that means we have a declaration of a couple. That means Kn, Kn1, Kn2, Kn3. If you have a declaration of a couple, That means for each node, we're having a vector k, and then at each branching node, we also have the same equation, kn equals kn1 minus kn2 plus kn3. But moreover, if we have we have a two paired leaves, if we have here we have another paired leaves, then this kn must equal to kn prime. Okay, so this is a requirement. It's because we're having paired leaf, then the for any declaration, the kn must equal to the kn prime, where n prime is a paired leaf at n. Okay, so this is declaration, and the b is another function, which is essentially the product of the two a functions that we see in the tree expansion. And finally, we have this product where here we are taking the product over all the leaves with a plus sign, but really it's just for any pair of leaves, if L is paired to L prime, if L is paired to L prime, then KL equals KL prime, and then we just take this input value, just take either one of them. So we just have one factor for each pair of leaves. That's it. Okay, so here the sign, this is scale, and this is actual factors, and these are product of the two a functions. And then this case declaration, where is the usual declaration in terms of the trees, and moreover, if you have a two paired leaves, then the corresponding k variables must be. So the main object we're looking at today is this expression. We'll see this again later, but expression, because this is the key thing we are seeing in analyzing this correlation. Okay, so we're summing over all the couples Q, all the trinity trees with all the possible pairings, and then among these couples, we are specifying a specific kind of couple which is called the regular couples, and these are exact notions that correspond to the main contribution in these asymptotics. Okay, so we define a regular couple. They are constructed by a very simple iterative manner. So we start with a trivial couple. Trivial couple just means we have two trivial trees with only one point. Okay, and then we start with a trivial couple, and then we repeatedly apply these two steps. Step A means we have two leaves, and then we turn these two leaves into branching nodes, and each has three leaves which are paired, with each other. Or we apply this step B, where we start with one node, leaf or branching node, and we make it. We add one more branching node and two more pairs of leaves in this manner. We call it the tree, and then we call it the tree last time. But this is a very explicit, operations, and we start with the trivial couple, and we repeat this operation, we get a so-called regular. Okay, and it can be shown. We don't have time to show this, but it can be proved that the number of regular couples is C to n instead of n factorial, which is the number of all the couples of scale n. And this is very important because that will allow us to avoid the key factorial divergence, which is one of the main enemies that we have in this proof. And moreover, last time we shown that the regular couples Q, the asymptotics of corresponding expression K2 can be explicitly calculated. We have this number theoretic argument, certain method argument that we can allow us to calculate four asymptotics. And moreover, for the regular couples, the four asymptotics will exactly match the solution to the equation. So we see that only those regular couples, they are going to contribute in the end, and their contribution is going to match exactly the weight gain. Okay, so now today we are going to discuss the rest of the.
I'm having difficulty hearing. I don't know if it's the quality of your microphone or it can be just me, but in case, do you have another audio means, or this is the only microphone you can speak through?
Is Is it clear now?
Well, I mean, for me, it's the same, but maybe some other people can chime in.
No, you think I have the same problem. I mean, maybe it's do you have the microphone of the iPad off? Maybe you have both on. It's a bit muffled.
I'm having audio from my iPad. I'm having audio from my laptop.
So one of them is it? It's just your voice is like muffled.
It's very
hard to
me. So as if something is covered the mic, so I cannot really hear. But
is it better now?
Welcome to check.
Is it better now?
I think so. It might be better now.
So, okay, so I'm probably getting closer to the laptop, so this may be better.
There is a little bit of feedback. That's why I was asking you if you have maybe both microphones on.
I'm not sure. But is it going on well now?
We can continue with what we have. That's fine.
I think it's better now.
Okay. I'll keep. Okay, so I'll keep.
I don't know if you want to try to switch microphones using the iPad for your microphone rather than the laptop. I don't know. If
it might be a better idea using
iPad. So
let's try the iPad because.
Recording in progress. So I should turn off the laptop.
You have to disconnect your computer.
Yeah.
Okay, so let's see. Wait a minute. So how should I
disconnect the computer? The iPad seems to work much better.
Okay, but now I need to turn off my audio for the computer. Sorry. Otherwise, it's
So you go to next to mute and you press the arrow and say leave computer audio, I think.
Yeah.
Okay. Good. Thank you.
Oh, this is much better.
Much better. Thank you.
Okay.
Thank you.
Okay.
Much better.
Good. Okay. So so we have what do we have here? So we have now we're looking at the non-regular couples. So we'll prove that all these KQs for non-regular couples, they are error terms. And the idea, as we explained, is to define an index for each non-regular couple index such that first of all, for any couple of scale n and index r, we're having this bounds. This expression bounded by delta to the n over 2 times delta minus CR, where C is a constant. So here the point is that the saturated bound for this KQ is delta n over 2, which is the ones you see in the Wave-Keenan equation. However, if you have a couple of index R, then you're gaining a big power L to CR compared to the worst case scenario. And moreover, the number of couples for scale n and index r is at most CR to factorial times C to n. And this is, with this, you can see that the total number of scales with a very bad estimate is only CR to the factorial, not Cn to the factorial. And unless r is equal to n, but when r is equal to n, you're gaining a big power of L. So this is fine. Okay, so once we find this R, then this will allow us to sum over this sum of all the couples, because if you have L to minus CR times CR to factorial, and CR to the factorial means CR to CR, and here R is less than capital N, which is less than log of L. So in any case, this sum is convergent. Okay, so the rest of proof will be looking at how do we get to how to define index and how do we get to these two results. Okay, so we start with the so-called structure theorem for non-regular couples. So recall the last time we discussed the structure theorem for regular couples. Essentially, it's talking about how we construct the regular couple from smaller regular couples. Now here's a similar thing. And now the structure theorem for non-regular couple tells us how to construct non-regular couples using regular couples. Essentially, is the following: for any non-regular couple Q, there is a unique prime couple, which is called the skeleton of Q, such that Q is obtained by replacing each leaf in the skeleton with a regular couple. Okay, so we have a picture in the next slides. Here, prime means that this skeleton couple QSK cannot be further reduced in the same way. That means QSK cannot be decomposed into regular couples. That means QSK does not have any subcouple which is regular. Okay, so this, you can think this QSK is a skeleton, so we'll call it a prime couple, and the Q can be constructed from this QSK by attaching like regular couples. Okay, in reality, we may also replace branching nodes of QSK by something we call regular trees, but the structure of the regular trees is basically the same as regular couples, and so this part is treated in exactly the same way as a regular couple, so we'll not talk about this part. Okay, so example of this structure theorem is the following. So the above one is a prime couple, which is called it's a skeleton of the lower couple here. So we have look at it. We have red is a pair of leaves. Blue is a pair of leaves. Green is a pair of leaves. So any pair of leaves in the above is two nodes with the same color. And in the bottom picture, we have two big circles, and each circle, each pair of circles with of same color means a regular couple. So this is a regular couple. So this is a regular couple. So we have a Q1 means regular couple. And we have another regular couple Q2, another Q3, Q4, Q5. Okay, so basically we start with the skeleton, which is a prime couple, and then we attach a regular couple at each leaf pair. Like here we attach a regular couple, 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 and then we recover the original couple. So that is the idea that any couple can be obtained from a prime couple by attaching a regular couple. So this is the structure theorem of non-regular couples. Okay, so now with the structure theorem, since basically we have a Q, which is a non-regular couple, and we have the QSK, which is skeleton, which is a prime couple, and then we have the QJ, which are regular couples. And then it is expected, since combinatorially Q is a combination of QSK with all these QJs, they turns out that in terms of analytic expressions, KQ, if Q has skeleton QSK and attached regular couples QJ, then turns out that the KQ can be expressed basically in terms of these KQSK and KQJ. So while the KQSK is not exactly the KQSK, but it's something with a slight modification that can be easily handled. Okay, so then this means that if we know the behavior of this KQJ and we know the behavior of this skeleton, which is a prime couple, then we will be able to deduce the behavior of a general couple Q. And since we already know the behavior of regular couples from last lecture, now it will suffice to look at the KQ for prime couples Q. And that is something we'll focus on for the rest of the talk. Okay, so again, we are copying the expression here. So KQ is this is some constant factors. We'll omit it, and then we're summing over all the decorations. So Q again, decoration means it's a decoration for each tree, meaning it satisfies a linear equation each branching nodes, and moreover for any two paired leaves, the corresponding vectors KL must be the same. And here we have having a function B here, and we have a product of this initial data, which is a Schwarz function. So let me explain what this B is. So, okay, so here we are having an extra. Okay, so what is this B? So let's say, so B is basically the following. Omega n is an integral of in the time domain, multi-dimensional time domain D of E product and here we have product of all these n e to the I omega n t n dtn. So here n runs over all the branching nodes for each n. Each branching node n, this omega n, of course, is a resonance factor at this branching node n. And then this Tn is time variables, and this domain D here is the following. Tn, such that the Tn bigger than Tn prime if n prime is a child of n. And Tn is bigger than 0, and Tn is bigger than T. Okay, so we have all these times Tn between 0 and T that satisfies a partial ordering that if you have the time variable corresponding to any parent must be bigger than time variable corresponding to the lead. So, but in practice, this is not important. It's really just a partial ordering. For example, like if we have this, I'm just drawing a random, couple here. Then we have 3 time variables because we're having 3, branching nodes here, here, and here. Then the B is like, in case B is like integral. So T, let's say T bigger than T1, this T1, this T2, this T3. T1 bigger than T2, bigger than 0. T bigger than T3, bigger than 0. And we have e to the I omega 1 T1 plus omega 2 T2 plus omega 3 T3 dt1 dt2 dt3. Okay, so this is basic expression of this B function. The exact expression is not very important. The only thing here is that it's an oscillatory integral in the multi-dimensional time variable dt1 dt2 dt3. Okay, so with this integral, it turns out that this iterated oscillator integral in the time variables, and for each integral, we're having a decay because if we integrate in T1, we get a decay in terms of a denominator involving omega 1. In the integral for T2, we have a denominator involving omega 2, and then we have a denominator involving omega 3. And each integral, we have a decay in terms of these oscillations. And when we take all these decay factors, it turns out that we can show that its coefficient B is almost L1 in the variables omega. And that is very important because that will allow us to reduce the end analysis of this KQ to a counting problem. Okay, so remember that here we're summing over all the decorations Kn, but then since this function B depends only on the omega, on the resonance factors, what we do is that we're going to first fix the value of the omega n of the resonance factors, and then so that we can sum over all these omega n using this B function, and then we are summing over the decorations Kn with omega n's being fixed. Okay, and for this to work, we need this B to be almost in L1, and that is what this oscillator integral gives us. Okay, so this is the next step. The next step, we are going to use this L1 integrability, which is also summability, because we're basically having a discrete time for a variable, and then we may then fix the values of omega n. And then we reduce the following counting problem. We want to look for the number of decorations Kn, such that for each branching node n, we have this, of course, this equation here. Of course, this equation is part of the requirements for the decoration. And then we have this omega n here, which is resonance factor at each branching node is like mod Kn1 square minus mod Kn2 square plus mod Kn3 square mod K minus mod Kn square is also a constant at each branching node. Okay, so this is the reason why we can make it a constant is because we are first fixing the values of omega n's using the integrability of the coefficient B. Okay, so then we are, you see if you look at this picture here, this is a constant, we forget about it, and then we're summing over this, and this is basically size 1, provided that each KL has a natural upper bound. This upper bound we're always assuming, and then now the only thing we're summing over is this, but then once we fix the value of omega n, then we are summing over these omega n's in the end. So we throw it away, and then we're just summing over the constant ones, and then that means we're reduced to a counting. Okay, so it's clear now we are reducing our analysis to this particular counting problem, and the rest of the talk will be looking at how do we analyze this counting problem. If the couple Q has scale n, then the saturated bound for this counting problem, which is bound we have in the worst case scenario, would be L to the d minus 1 times n, which is consistent with this factor here. Here we have L to d minus 1 times n, and it turns out that we have a delta minus n over 2 factor here that cancels part with this, but we'll not worry about too much about the delta. So here the power of L is L to d minus 1 times n, and that is what we also expect in this count. Okay, so L d minus 1 times n, and turns out this bound is saturated exactly by the regular couples. And for our goal, of course, since we are not satisfied with this, we want to get some extra gains in terms of power of L, and that is, say, we need to prove something of this form, L to d minus 1 n minus CR, where R is the index, which will be defined later. Okay, so now how do we study these counting problems? So a key observation here is that the counting problem is a big counting problem involving many variables and many equations. However, it is formed by the local counting problems, where each local counting problem involves what we call a local family containing a branching node n and its 3 children, n1, n2, n3. This is very clear here. For each branching node n, we have one linear equation and one quadratic equation. And this is what we call local counting problem. For the local family contains the variables kn, kn1, kn2, kn3 for each of this n, n1, n2, n3. Okay, so a natural strategy to study this counting problem is we just study one local counting problem at one time, where of course we count the number of choices for kn, kn1, kn2, kn3 once at a time. However, there are 2 issues with this approach. The first issue is that recall that in declaration kn, we must have kn equals kn prime for paired leaf n and n prime. So we have if we have a leaf, for example, if we have a leaf, this is, for example, if this is a leaf, they are paired, then we have kn equals kn prime. Notice that they are paired leaf. The leaf pairs are arbitrary, so some leaf may pair with other leaf that is very far away from it, and this creates a non-locality. That means if we fix kn in one local family, in one counting problem, then this may affect the behavior of another local family, local counting problem in a very far away place, and that is something we don't want. And another thing we don't want is that if we just try to do the induction, try to remove the counting problem, remove the local family one by one, then if we start with a couple and remove a local family, then this will not remain, the couple will not remain a couple, which means that we cannot do induction. Okay, because the structure of couple, if we remove like these 4 nodes, then we'll not have a couple anymore. So these are two serious problems that we will try to use this natural strategy of doing induction, doing the counting problems one by one. And the way to solve these 2 problems is by introducing a new structure, a more flexible structure, which we'll call molecules. Okay, so the definition of molecules is on next page. So here we introduce a new structure which we call the molecules, and it's much more flexible and much more robust than working with couples. So basically here, by a molecule, we mean a graph where the degree of each vertex is at most 4. So this is like the carbon atoms in the organic chemistry. So we're calling it molecules. So we construct the molecule from any couple, which will we'll show a picture next in the next slide. So basically, the idea is that the vertices or the atoms in the molecule are the local families formed by one branching node Kn and the children N1, N2, N3. So for each local family, we have atom or vertex. Okay, and two atoms are connected by one or more edges or bonds if and only if the corresponding local family have one or more common elements. So again, we'll show an example on the next slide. Notice that if we have two paired leaves, N and N prime, then Kn must be equal to Kn prime. So then in the corresponding local families, these paired leaves also count as the same as a common element for this purpose. Okay, so and then once we transform the couple into a molecule, and then declaration of couples is then transformed into declaration of molecules. While here it turns out that each node in the couple corresponds to each edge or each bond in the molecule M. And so for the declaration here, we're assigning a vector KL to each edge or each edge L in the molecule, and then for each vertex, for each atom V, we have local counting problem. We have a system of equations, just as the equations we're having here. This system we're having here for each here having the system for each branching nodes, but in the molecule picture, we're having each having a system for each vertex. Okay, local counting problem involving the algebraic sum of KL of the vectors and mod KL squares for edges L at this V. Okay, so this idea, this transformed molecule, it solves both of the two difficulties which we just mentioned. First of all, because now if we have two paired leaves, they are far away in the original couple, but they are very close in the molecule picture because the two paired leaves correspond to one edge in the molecule. They are very far away, but they're really just correspond to one edge in the molecule by definition. And second, if we remove a few atoms from the molecule and remove corresponding edges, the molecule will remain a molecule because it's a much more flexible definition here. It's just a graph where each vertex has a degree at most 4. Okay, so let's look at an example of a couple and a molecule. So here the upper half is a couple, is a prime couple here. It has 4 branching nodes. This one is marked 1, 2, 3, 4. And then 4 branching nodes means we have 4 local families. Recall that each local family is a branching node and 3 children's. And so we have 4 branching nodes and we have 4 local families. This one is 3 children, and 2 with 3 children, 3 with 3 children, and 4 with 3 children. And they are the 4, this corresponds to the 4 atoms in the molecule. So here 1, 2, 3, 4. And now let's say we have an edge between 1 and 2, because in 1 and 2, we have a common element, which is let's draw this one here, right? 1 and 2 have, the 2 local families at 1 and 2 local families at 2. They have one common element, which is this one. So we have one edge between 1 and 2. And here we're marking this. Okay, so anyway, so we're marking this. Yeah, we're marking this as A, and this edge is marked as A. Okay, this represents this edge represents this common element A. Okay, and similarly, between 1 and 3 here, there is another common element, which is C here. And then we have another common element because a leaf here is paired with a leaf here. So we have another common element marked by B. Okay, so there are 2 edges between 1 and 3 marked by B and C. Okay, and similarly, there is 1 edge between 2 and 3. 2 and 3, we have, we have one common element marked by this leaf pairing. So this is marked, maybe we can expand it. So this is marked by E. So we have a edge between atoms 2 and 3 marked by E. And similarly, we have an edge between 3 and 4 marked by G. 3 and 4 here marked by G. And then we have 2 edges between 2 and 4 between 2 and 4 because we're having this this D here, D with D and F with F. So we have 2 edges here between 2 and 4 marked by D and F. Okay, so this is how we transform the couple into a molecule. So this a graph with degree 4. So in reality, these edges are directed, which indicates the signs plus and minus, but this will not play a key role, so we'll not show it in this picture here. Okay, so then you see, for example, you know, this node here is paired with is a leaf which is very far away, but really in the, if we transform to the, you know, to the atom picture, it just both of them correspond to this particular edge A in the atom, which solves the non-local problem. Okay, so this is the we transfer into atom, and now we are looking at the counting problem for the atoms. And the counting problem for the atom is very simple. For example, we are having a variable A, B, C, D, E, F, G, and then for each atom, for example, for the atom 1, we have an equation, plus minus A plus minus B plus minus C is constant. Plus minus A squared plus minus B squared plus minus C squared is constant. So this is the equation for 1. And the equation for 2, for example, we have a plus minus A squared plus minus D squared plus minus F squared is constant. And plus minus A plus minus D plus minus F equals constant. Okay, so this very, sorry. It's very simple transform from couple to molecules. Okay, so now we can state the main rigidity theorem, which is the main result we're having for the counting problem for molecule, which is main results, main technical result of this proof. So let M be a molecule that is obtained from a couple Q. I should say, assuming Q is prime. So M is a molecule that is obtained from a prime couple Q. Then there exists R, which is called the index of Q, such that first, if we have an index R, then this molecule has a very specific structure. It must be formed by at most CR chains. These chains have type 1 chain, type 2 chains. We'll see this on next slide. And moreover, those atoms in not only on one of these chains has at most CR other vertices, at most CR atom. So think R is very small compared to N. And then this is a very special form. It has at most CR chains. These chains have very explicit expressions. And then we have other vertices, but we have at most CR other vertices, very few other vertices. Okay, and moreover, the counting problem for decorations over M, so that we already explained in the last slide, this counting problem has upper bound L to the D minus 1 M minus CR for some positive constants. Okay, so you see we are gaining a power L to CR in the counting problem, which is what you want. And then on the other hand, if we fix R being big, then we're gaining a lot of powers. If we fix R being small, then there is very, very few possibilities for the molecule M. And then also for the couple, which since we can actually recover the couple from molecule up to a few, harmless factors. Okay, so this is the theorem, which tells us that really if you want the counting problem to be saturated, you're close to the counting problem for the regular couples, then there is very, very few possibilities that the atoms can be, which is what rigidity means. Okay. So what are the type 1 and type 2 chains? So these are type 1 and type 2 chains. So these are type 1 chain. We have a double bond, double edge between 2 adjacent molecules, and we have these extending chain. Note that each atom here, each vertex here already have degree 4, which is saturated. So recall that in the molecule, any atom has degree at most 4. Okay, so then for example, this type 1 chain cannot be connected to anything else by any means because it's already saturated. Okay, so this is type 1 chain, and type 2 chain is slightly different. Now we have a double bond, double edge between these two and a single edge between these two, and we extend it like this. Notice that again, like all the atoms here have degree 4, so they are saturated, they cannot be condensed. So which means once we have a type 1 chain or type 2 chain, they must be separated from the rest of the molecule. Okay, so know that, and moreover, these type 1 and type 2 chains have very explicit expressions. So it turns out if we want to add most CR type 1 or 2 chains to a molecule size CR, which is the statement in our rigidity theorem, then the number of choices we have is the most CR to factorial C to the N, and the same for couples. This means that once we prove the rigidity theorem, then we know the number of choices of couples of index R is at most CR to factorial C to N, which is the thing we are expecting in our plan. Okay, so this is the rigidity theorem. So now let us briefly discuss how do we prove this theorem, like how do we define this index R and how do we prove this theorem. So the idea is the following: we'll be studying the local counting problem now, not for the couple, but for the molecule, and local counting problem at each vertex, at each atom of the molecule. Basically, you see, we need to study the local counting problem at one, atom. So it has degree 3 or maybe degree 4. Never mind. So we have this. We have V1, V2, V3, V4. So this is a picture in the molecule. We have L1, L2, L3. Then we have KL1 plus minus KL2 plus minus KL3 equals constant. And you have a square equals constant. So this is the local counting problem. In some cases, we need to consider the local counting problem at 2 vertices. That means, for example, if you have this, if you have a molecule look like this, so you have a L1, L2, L3, L4, L5. Then we have L1, KL1. KL1 plus minus KL2 plus minus KL3 equals constants. And then we also have this, at this atom, we're having this equation. At this atom, so we're having another equation, which is KL3 plus minus KL4 plus minus KL5 equals constant. And then we have the square plus 1 quadratic equations. So we have this system, which is also we view as a local counting, local system, for the countings. And these leads to basic, what we call the 2-factor counting problems, 3-factor, 4-factor, 5-factor counting problems which will be the building blocks of our proof. So here we use a simple notation ABC in S to denote that we have these 2 equations, A plus minus B plus minus C equals constant, mod A squared plus minus mod B squared plus minus mod C squared is constant. And the same if we write AB in S, then we mean that we have the equation for the 2 vectors. Okay, so for example, in this problem, we're having a counting problem involving 3 vectors, which will be a 3-factor counting problem. In the left picture here, we have 5 vectors involved, and we'll have a 5-vector. Okay, and the next slide will explain we introduce the basic results for the counting problem, which is really just kind of elementary number theory. So first one, the 2-factor counting, we're counting the number of vectors A and B, such that A, B belong to S means A, B satisfy the 1 linear equation, 1 quadratic equation. And the bound for number of choices of A, B is L to D minus 1. Okay, it's 2-factor counting. And now 3-factor counting, we have A, B, C belong to S, A, B, C satisfy an equation, and then the bound here is L to 2D minus 2. Okay, so this bound can be proved easily using mostly n-dimensional number theory, and in a few cases we use circle method, but it's mostly n-dimensional. Okay, and 3 we have a 4-vector counting when we have ABC satisfy an equation and AD satisfy another equation. Then the bound we have is L to 2D minus 2 minus 1 over 4. And here this is colored blue because later on it will be a good case that will gain us some powers. Okay, and similarly, we have another case for 4-vector counting. 4-vector counting, we have ABC satisfying 1 equation and ABD, let's say, satisfying another equation, and then bound is the same L to 2D minus 2 minus 1 over 4. In fact, if we subtract the 2 equations, you'll get ABC satisfying 1 equation and CD satisfying another equation, which we can reduce to the case 3. But in any case, the bound here is the same as case 3. And finally, we have the 5-vector counting, which is a picture we're having here. You see, we have 2, 3-vector counting problems with one common element, which is L3. right? So then we have ABC satisfying one equation and ADE satisfying another equation. And the bound here we get is L to 3D minus 3 minus 1 over 4. Again, this will be a good case I will show later. The proof is basically elementary number theory. And notice that the last 3 bounds are good, while the first 2 bounds are normal, which you'll see immediately what they mean. Okay, so these are the building blocks, the tools we're using for the counting problems. And now what we do with our molecule, we'll just try to, again, reduce atoms or molecule, remove the atoms or molecules until we reduce the molecule to empty. And we do these counting problems in this process. Okay, so we may define different reduction steps. Turns out these steps have to define specifically. In some cases, we remove 1 atom. In some cases, remove 2 atoms. In some cases, remove 1 atom and remove some edges and add some edges. So it depends on the exact local structure of the molecule. So we have defined different reduction steps. We're starting from a molecule, repeatedly apply these steps until the molecule becomes empty. And these specific defined reduction steps, there are about 20 different steps, and some of them are normal, some of them are good. We'll see later. And most of these steps involves removing 1 or 2 vertices and the corresponding connecting edges. Okay, so it's basically think of as we either remove 1 vertex or remove two vertices. Okay, so this is the thing we'll do for our molecule. And in this process, we'll keep track of the power gamma of L in the counting assay. That means we'll do the counting estimates in this process, as well as we have to keep track of the so-called characteristic chi, which is E minus V plus F of the molecule. So combinatorically, this chi basically means the number of independent cycles in the molecule. If F equals 1, chi is 0, then we have a tree. Otherwise, we have some cycles, and the chi is number of independent cycles. So here, E is the number of edges, V is number of atoms or vertices, and F is number of connected components of molecule. So basically, we're going to compare this gamma with this chi. So in the end, we have chi equals gamma equals 0, which is when the molecule becomes empty, this is 0, there's no counting assay, and everything is 0. Initially, you can calculate chi is equal to n, and gamma is what we want to control. And as such, we're going to keep track of the increment of this quantity, gamma minus d minus 1 times chi. Okay, and we'll see that the increment of here, this is either positive or 0. Okay, and now let's look at the step. Let's look at 2 examples. One example of a normal step, one example of a good step. So look at the following step where we start with the degree 3 vertex, degree 3 atom. This has degree 3. And it's 3 edges, this. We're marked with A, B, C. And then we remove them. Okay, we remove this atom and remove these 3 edges, and we're reduced to this. So here we're assuming that these are interconnected so that this doesn't add the new connected components. Then we can calculate that we are reducing like 3 edges. We're reducing 1 vertex with not changing the components. So then we have minus 1, minus 3, minus 3, minus 1, 0. So the chi decreases by 2. Okay. Now, on the other hand, by the 3 vector counting problem, if we have this picture, then ABC will satisfy 1 equation. So ABC belongs to S. Okay, because it satisfies the system of 1 linear, 1 quadratic system. And then, so then we want to know how many choices do ABC have? The answer is L to 2D minus 2 by the 3 vector counting problem. And now once we fix the values of ABC, we can effectively reduce, once ABC is fixed, we can effectively reduce the counting problem for the reduced molecule, for the smaller molecule, because this ABC are fixed, we no longer need them. Okay. And then this means that this gamma here is minus 2D minus 2 because we are moving from a big counting problem to a smaller counting problem. And the difference between the powers is minus 2D minus 2. And we can calculate that this increment of this quantity, gamma minus d minus 1 times delta, is 0. And so we are calling it a normal step. So this is example of a normal step, and now look at example of a good step. So I'll be finishing soon, like in like 5 minutes. So the following step here, we're removing 2 degree 3 atoms, vertices connected by a single edge. So this is degree 3, this degree 3. They're connected. You have 5, edges A, B, C, D, E. Okay, and then we're removing them means that we're removing all these. We're left with the rest. And again, assuming here these are interconnected. These are interconnected so that we don't add the new connected components. Then we can have the E. We remove 5 edges, 2 atoms, and no components. So then delta chi is -3. So we have delta chi equals -3. On the other hand, again, we look at the possibilities for the vectors A, B, C, D, E. Then we have A, B, C belong to S, A, D, E belong to S, means we have an equation involving A, B, and C for this atom. We have another equation involving A, D, and E for this other atom. And then we have this, which is exactly the 5-vector counting problem we are having. And so by the result of 5-vector counting problem, we know that the number of choices for A, B, C, D, E is this, L to 3D minus 3 minus 1/4, because it's 5-vector counting problem. And once we fix A, B, C, D, E, we can reduce a smaller counting problem of the reduced molecule. And so the increment of gamma is this minus, so this should be minus 3D minus 3 plus 1/4. Now we see that this delta, the increment of gamma, is bigger than d minus 1 times increment of chi. If you look at this, if we compare these two numbers, then the increment of this is positive. And then we have good step. Okay, so these are definition of normal and good steps depending on whether the increment of this is positive or 0. Of course, you may ask whether there are bad steps, where the increment of this is negative. The answer is no. Like for every step we have is either good or normal. Either the increment is 0 or the increment is strictly positive or bigger than a positive constant. Then, of course, this is a very good case because the thing we do here is that we just need to find a sequence of steps with as many good steps as possible. Again, there is no bad steps, because if we know if we have many good steps, that means the total increment of this gamma minus d minus 1 chi is very big. But then in the end, the gamma is 0, the chi is 0. So if the increment is big, meaning the original value of gamma has to be smaller than something, has to be having upper bound, and that is exactly the upper bound for the counting problem that we want. Okay, so then the goal is to find a sequence step with as many good steps as possible. And turns out it's a very simple, conceptually very simple. We just do a greedy algorithm, like whenever it is possible, whenever it's possible to do a good step, we just do a good step. And if it's no possible good step, it turns out in this case, the whole molecule must have very specific structure, and then one can do a normal step, and then we keep looking for good steps. And then in this way, there is a combinatorial proof that tells us in this way we can indeed get the many good steps we want. Okay, so here if a couple Q being prime, that means this molecule has no triple edges, which is important for the algorithm. And moreover, these type 1 and type 2 molecular chains are actually obstacles in the sense that within these molecular chains, type 1 and type 2 chains, we only have normal steps. However, they are the only obstacles. That means once you get rid of type 1 and type 2 chains, there is a combinatorial argument that shows you must have a lower bound for the good steps. Okay, and then this is idea, and the algorithm is it's too complicated to describe here, but essentially it's like we just look for good steps. If there's no good step, then we must have some very specific structure, and then we can do some analysis for the molecule, and then in the end we can show that the molecule must have a very specific form. Okay, so finally, let's look at the type 1 and type 2 chains. So these shouldn't be a problem because they are very specific objects. It turns out type 2 chains are fine. They are very not hard to analyze. And type 1 chains, they may lead to logarithmic divergence. Recall that the coefficient B, we say that's just almost L1, not exactly L1. However, in the case of type 1 chains, it may become problematic. However, it can be shown that type 1 chains in the molecule only come from so-called irregular chain, which is this form here. You have a chain here, but then you have a sibling of a node paired with one of its children. Such pairings. And these kind of irregular chains, it was already observed in earlier works in the earlier works of our earlier work on the subcritical problem, and also in the earlier work of Collatz and Germain. There we noticed that there is a formal divergence of the absolute value of corresponding expressions. However, there is a key cancellation between the different choices of irregular chains, which is also crucial to our proof that if we want to, complete the proof, that if we look at the different choices of irregular chains, for example, here, these are two irregular chains, right? And then the difference here is that whether, in the left chain here, we're branching at this N1, here is the left child of N0. And here the N1 prime branching node is the middle child of N0 prime. And then we can shift, either we branch on the left or we branch in the middle. There are all these possibilities. And turns out that the only difference here is the location of branching nodes for these. There are more different like irregular chains. And these different locations leads to different signs. So they have different signs. On the other hand, the other parts of the expression, the otherwise the corresponding expressions are almost the same, that the coefficient is the same, the input function is almost the same with errors which are controlled, which can be well controlled. And then once we combine all these things, we have the expressions almost the same, but then they have different signs. So then we see a cancellation. And this cancellation allows us to treat the type 1 chains, the irregular chains, and it allows us to treat the type 1 chains. And then this together with the molecule analysis will allow us to complete the proof that all these non-regular couples give negligible contributions. Okay, so we'll stop here.
Thank you. Thank you very much. Very nice, clear lecture. Any questions? Okay. Well, in this case, I think you one more time. Oh, Claude, you have.
Hey. Okay. Thank you a lot for this very nice talk. So you just for you to repeat what you just said, but so this last chains that you said were irregular.
Yes.
So in fact, so there is a cancellation. So in fact, they do not contribute. I mean, in the end, when we sum over all possible such irregular chains at some point in the graph, then it cancels.
Yes.
Oh. Is there an explanation which is okay, more, I don't know, not just combinatorial, or is there an intuition behind that? Or?
I'm not sure, but this cancellation is actually a little bit subtle because it also requires some conditions on the declaration, the difference between two particular vectors being small, and in the case of difference being big, it's a different treatment. But I think
yes, I mean, it's a low frequency problem somewhere. So okay,
yes.
I mean this.
So I'm not sure actually. I'm not sure. So, but I have interesting, one interesting thing is that this cancellation seems to be a little bit problematic in the, irrational case where we assume the kinetic time scale is bigger than L squared. It works perfectly when the kinetic time scale is less than L squared. If its kinetic time scale is bigger than L squared, there seems to be an issue. So I don't know. It probably has to be like the universal phenomenon. It doesn't depend on the shape of the torus. And whether there is an explanation, I think if you believe the approximation, the wave kinetic equation is true, then kind of has to be so, but
Yes, but you know, like this belief that the wave kinetic equation is true is based on less sophisticated analysis than
yes,
what you did. So
yeah. So I only have the combinatoric explanation.
okay. But so okay, in fact, this is a question that I had regarding a previous talk of Zaher, is that with this, this is why you are able to reach the kinetic wave equation, but for times which are less than L square. Like
Yeah, so okay, so currently we can get to the kinetic time scale, we can get a result for, let's say less than L square, bigger than L to the 2
We don't
minus
see, you're
power
not
100.
sharing you're not sharing your screen.
Oh,
so-
sorry. Let me share it again. Let me share it. So let me say that currently we have the result for L to the 2 minus epsilon L square. So this is okay for all tori and for irrational generic.
okay,
So epsilon, let's say 1/100. So this is what we have currently, and we expect we have a 1 less than L square is true for all
okay.
tori, like between 1 and L square. And now the question is,
But so
bigger than
just
L
so
square.
this 100 is like 1/100. It's due to this problem of irregular chains, or it's due to something else, and in the end you have like too many.
I think it's just a technical requirement for the proof. Like if we refine the proof, we should be able to get to this full range.
Okay.
Okay, and T bigger than L square, this we don't know for now.
Okay.
Okay.
Oh.
Great.
Okay.
Yeah.
Thank you very much, you for answering the question.
Any further questions? Okay, so in this case, thanks you again. Very nice talk, very clear. And we will not have a meeting next week because there's the summer school next week. But you will get an announcement when they will meet again. So hope to see you soon. Take care, everyone. Thanks you. Bye.
Bye.